Hello. Hi everyone.
Hi, good evening, ma'am.
Yeah, good evening. Uh, so how many of you gone through that APB protocol code in system Verilog?
Yes, ma'am.
Hmm? Did you understood all the blocks?
Ma'am, scoreboard alone I can't understand, ma'am, because I don't know which we are going to compare with.
Hmm. Okay. In this scoreboard, we didn't written any logic to compare. Just it display the output. That's it.
We need
It
to
is
write
not.
or this is the logic, ma'am.
We can write the comparison logic also. We can generate the reference values and we can write.
Okay.
Here I have not written, but before examples we have seen, right, P4
Yes,
in
ma'am. Yes.
system block. There we have written in calculator project also we have written. So like that you can try. Just how you will check write address and read address must be same. Write data and read data must be same. That condition you need to put. Okay. Others, do you have any doubts in APB protocol? In the end of the session, we will discuss again the code for APB. Meanwhile, first we will start with the assertions. Okay, so coverage topic completed, right? All type of coverage pins and how practically we can write the coverage. Okay, so do you have any doubts in the coverage? I have shared the assignment on coverage, right? Have you practiced that?
Yes,
Some
ma'am.
interview questions on coverage. So, how are the questions? Hmm? Are they helpful? Mostly those are interview point of view only. As a fresher, no need to concentrate much on coverage and assertion, but these are very important topics. Okay, even if you go for industry or if you get some experience, 3 year, 4 year experience, that time these coverage and assertions are most important. But if you are fresher, you won't get much questions from coverage and assertion, just basic questions. Okay, but you must have the depth knowledge that is good. Okay, so today we are going to discuss on assertions. Assertions also one of the most important topic and advanced concept in system dialog. Okay, so first of all, what is mean by assertion? Do you have any idea? What is mean by assertion?
We can validate the behavior of our design.
Okay, we can validate the behavior of a design. Okay, so how we can do that? How can we validate the design? What are the methods? What are the different types of assertions? Hmm?
And we
Somebody?
can write the assertion as yeah, we can write the assertion as per the functionality of our design. If that particular functionality met, then the assertion goes high. Otherwise, it goes low.
Okay. Tamilarsan, have you gone through the coverage sessions and assignments? Hello.
You are asking it to
Uh,
me.
No, not you. Yeah.
Prashanti, like I couldn't hear you because I connected in mobile data actually. I,
Okay. My voice is not clear.
no, only like I can hear only little bit. I can't hear you couldn't because like I don't have Wi-Fi connection today.
Okay, okay,
And
fine.
you are
Have you gone through the coverage sessions and
yes, actually
assignment?
I'm going like coverage sessions. I'm going through. Like I didn't start any session.
Okay, 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 fine. I also shared the coverage assignment, so just work on that. If you have any doubts, please let me know. Okay.
Okay.
So, what is mean by assertion? So, as he said that assertion specifies a behavior of the system. Just we validate the behavior of a design. Okay. So, how we can validate the behavior of a design? Suppose any example, if you consider sequential logic circuit or counters or even gates. Okay, for gate also at point of like 0 0 0 1 1 0 1 1, we have some condition, right? And gate means what is for 0 0 and 0 1 1 0 1 1. If you take any sequential logic circuit at the particular clock trigger, at some positive edge of the clock or at some reset, what is the output, how the output is triggering. So every positive edge of the clock we need to check how the output is triggering. Okay, so we will validate the design using the assertions whether the design is working properly or not. We can do that using the assertion. Okay, you may get the doubt what is the difference between coverage and assertion. Okay, basically coverage is just to confirm the verification is done or not through the coverage report. Okay, so we will check the functionality of the coverage, how much functionality we have covered, okay, through the test cases and coverage bins. But assertions are written for the design, not for the test bench. Okay, so for design point of view we write the assertion to validate the behavior. We'll see some examples so that you will get the clarity. Okay, so in addition, assertions can be used to provide the functional coverage and generate input stimulus for validation. And also evaluation of assertions is guaranteed to be equivalent between simulation, which is event based, and formal verification, which is cycle based. Okay, event based means here to execute any instruction, any code, any line, it follows some event, that means event regions. So at what time which statement should execute, like we have active region, inactive region, prepone region, postpone region. In test bench and design we have different type of blocks, right? Non-blocking assignment, blocking assignment, and loops, always blocks, procedural assignment statements, continuous assignment statements. There are different blocks out there. Okay, so every block execute at some event regions. Okay, some blocking assignments will execute in blocking region, non-blocking assignments execute in non-blocking region. Like that, some statements execute in active region, some are in prepone region. Like that, we have different regions. We will discuss in the next session. Okay, so assertions are basically execute in that format. Okay, and system verilog allows assertions to communicate information to the test bench and allows the test bench to react to the status of assertions without requiring a separate API, application programming interface of any kind. Okay, we don't require any interface and all. Directly we can communicate with the test bench and also with the design. Okay, and mainly advantages of assertions are improving observability, and it reduces the debug time, because in the design we will do the debug directly using assertion, so that we can capture easily how and where the some uh, condition is not working. If any condition doesn't work, we can check easily with assertion. No need to write the test cases and all. Okay, directly we can check with assertion. And big bugs can be found earlier and more isolated. and controllability severity level, and can interact with the C functions. We use DPI also, and describe the documentation and specification of the design. Okay, so these are the advantages of assertions. And in assertions, we have different types. One is immediate assertions and concurrent assertions. Okay, so if you observe what is the assertion, like assertions are primarily used to validate the behavior of a design, and assertion is checked embedded in design. That means we write in the design, or bound to a design unit during the simulation. Okay, warnings or errors are generated on the failure of a specific condition or sequence of events, because in the assertions we will write some conditions, error condition, some fatal error condition, or execution successful or failed. Okay, so those type of conditions or warnings will be generated by automatically generated by assertions. Okay, and we have two types of assertion, different kinds, like immediate assertion and concurrent assertion. Immediate assertions are nothing but these are evaluated once. Okay, typically within a procedural block, we write within a procedural block. You already know initial, always, final. These are procedural blocks and are commonly used for checking the condition that should be either true or at a specific moment. Okay, either true or false. Next, concurrent assertions. Concurrent assertions are evaluated over time and are used to specify temporal conditions. Okay, they monitor sequence of events and are ideally for complex conditions and unfold multiple clock cycles and all. We use the concurrent assertions. Okay, both are used mostly. Immediate assertions we use mostly in the test benches because those are used in the uh, procedural blocks, right? So if you see here, immediate assertions checks for a condition at the current simulation time. Okay, so immediate assertion is same as a if else statement. You can write the immediate assertion, or else we can write a if else statement also. Both are same. Okay, and immediate assertions have to be placed in a procedural block, as I already told. So if you see the syntax, okay, so label, assert. Immediate assertions means we mention with assert of expression, action block. Okay, and the optional statement label, it's just a identifier, just a name of the assertion, creates the named block around the assertion statement. The action block is executed immediately after the evaluation of the assertion, and the action block specify what actions are taken upon successful or failure of the assertions. Okay, that means we will write if the condition, that means if the expression is successful, what the statement should display. If the expression is fail, what is the error, fatal error. Okay, that thing we do in the action block. So if you see here, action block, it specifies pass statement or else fail statement. And just go through the theory, whatever explained, same thing. The pass statement is executed if expression evaluates to true. Fail statements means expression evaluates fail. Um, and we write different system task here, simulator directives like dollar fatal, dollar error, dollar warning, dollar info statements. Okay, these are different statements we use in the assertions. And one of the example in assertion, for immediate assertion, always at the rate of pausage clock, assert A and B. Okay, so A and B true means we get pass, 0 means fail. Okay, we can write that expression also here, but this is what the format syntax for immediate assertion. Okay, always at the rate of pausage clock, assert A and B. So condition A and B will checked at every positive edge of the clock. Failure in the condition leads to the assertion failure. Okay, so it checks for every positive edge of the clock. Here at every positive edge of the clock, and what are the inputs A, B. So at this positive edge of the clock, A is 1, B is 1. So at this positive edge of the clock, both are 1. So high, output is high. So pass. Like that, 1, 0. Output is 0. So fail. And 1, 0 or 0, 1. Output is fail. 1, 1. At this condition, output is pass. Okay. Like that, we will check every circuit, like event shift registers or counters. Okay, so whatever the design we are writing, it check every point of time, every positive edge of the clock. Okay, so that we can easily point out where the error is getting. So where we are getting some functional bugs and all, we can identify easily. That is what assertion. And concurrent assertions. Okay, concurrent assertions check the sequence of events spread over a multiple clock cycles. And concurrent assertions are evaluated only at the occurrence of clock tick. The test expression is evaluated at clock edge based and sample values of variables involved. Okay, so it is placed in the procedural block. So what is the difference between concurrent assertion and immediate assertion means just here in terms of syntax. Assert property. In the concurrent assertion, we will write assert property. In immediate assertion, we just mention assert. Okay. So at the rate of posage clock, not A and B. Okay, not of A and B. It check. So these are what the difference between immediate assertion and concurrent assertion. So we will check some. We will look into some examples. Do you have any doubts still here, everyone?
Hello, ma'am. Can you please explain concurrent assertion once?
Yeah. So concurrent assertions means it check the sequence of events. That means what? In a flow, it checks a flow. Example, suppose like immediate assertion means it checks the behavioral, like wait, let me take one example so that I will explain clearly. So this example is for immediate assertion. Okay, so immediate assertion here, what is the statement design? So here we consider one design, counter design, a 4-bit counter with an overflow detection mechanism. Overflow in the sense 4-bit means it counts 0 to 15. If it reaches 16th clock cycle, it should reset to 0, right? So here immediate assertion in this test bench to check the counter reset behave the correctly or not. Okay, so whatever the reset we are applying, whether the reset is working correctly or not. Okay, so the reset should immediately set the count to 0. For that purpose, we are writing the immediate assertion here. Okay, so we will check the counter reset operation by using immediate assertion. Counter logic, input and reset and count, output count. So at the rate of posage clock and negates reset, if reset is 0, count equal to 0, active low reset. And else if count equal to all ones, then count equal to 0, reset on overflow, else count equal to count plus 1, do the count from 0 to 15. Okay, simple counter logic, up counter. So for this counter, how we can write the test bench assertion? So module, counter, input and output declaration, and DUT, and count clock equal to 0. By using forever, clock is generated, and initial begin, starting counter reset equal to 0. Immediate assertion we can write in a two ways. By using if else condition we can write, by using the syntax syntax we can write. Okay, so if you see here, if count is not equal to 0, then dollar fatal, immediate assertion failed, counter not reset to 0 after reset n is deasserted. Okay, so it should go to 0 after reset is deasserted. So if it is not go to 0, we get the error. Else immediate assertion passed, counter will uh, do the counting operation from 0 to 15. Okay. So next, if reset is high, whenever reset is high, it display the end of counter. Okay. And this is for just if reset is high, it display the counter value, because here active low reset, right? Reset 0 means counter will go to 0 operation, or else it do the counting. So immediate assertion is written using if condition, if else condition, or else we can also write in this format.
Where are we writing the assertions, ma'am? In design or test bench?
Immediate assertions we write in the test bench, concurrent assertions we write in the design, or we can write in a separate file also for assertions. Mostly we write within the procedural block, right? We can write in any procedural block. So here immediate assertion means it just check the condition. Okay, so I will show you how another way we can write. Suppose if you take this syntax, how we can write the immediate assertion for same example, for same count example. Can you tell? For same count example, how we can write the immediate assertion. Hmm?
Ma'am, if dollar fell reset, then implication count is equals to 0.
I'm writing here. We can also write assert count equal to 0. Else, here we get the fatal error. We can write the fatal error. Dollar fatal, what error we can write? Reset is failed. That means count is not 0 after reset. After reset. So this is how we can write very simple assertion using immediate assertion. Both are same. This logic is same, or in place of direct assert logic, you can write the if else also. As you see in the statement, immediate assertions nothing but if else. Both are same. Okay, we can write using if else also. Clear everyone till here? So here in if else condition, it will check the when count is equal to 0, it will do the count operation, else it do the reset operation. I mean, it give the error. Okay, so here it runs the assertion immediately and verify the count is 0 or not. No need to write any extra files, like in coverage we have written run.do files and all, right? So here no need to write. So we can check.
So both if statement and assert, the two are same, ma'am, same operation.
Both are same.
Okay.
You can write either this or this. I will do both simulation. First I am checking with if, then we'll check with this statement also. Okay. So immediate assertion passed. First we got immediate assertion passed. What we have written here, count is not equal to 0. Count is not equal to 0. So assertion passed, it can count from 0 to 15. So counter reset to 0 as expected. So counter value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ending counter test bench. Okay, 10 to 15. Because here we have written ending counter test bench after releasing. So counter 0 to 15 and after 15 0 to 3. You can check the waveform also. So let me write or just remove this display statement. Dollar fatal system. Okay, it's loading. You also can check. Okay, afterwards I will share the code link. Just check from your side. And coming to the concurrent assertion. So what is the difference between immediate assertion and concurrent assertion? Immediate assertions means at every positive edge of the clock, it check for the condition is true or false. Okay, but concurrent assertion means it ensures that overflow detection work correctly or not. Based on concurrent assertion will check that whenever the count reaches 15, it should set to 0 on next clock cycle. Like overflow, it will check, okay, every clock. So here concurrent assertions we will write in the design itself. No need to write in the test bench. So module counter clock reset count value and previous count just temporary variable, and always at the rate of posage clock and reset. If reset is 0, count equal to 0, and previous count also initialized with the 0, else previous count equal to count, assigning the count value to the temporary variable. And if count equal to all ones, it should set to reset, else count equal to count plus 1. Okay, so how we can write the concurrent assertion for overflow and also for sequential increment. Here it will check with overflow and also increment check assertions. Okay, so can anyone explain here how it's working? Hello, fast. How the overflow is working and sequential increment.
Yes, at the yes, at positive age of the clock, if count value is 111 means 16, then it makes the count equal to 0. So when this property assert, it will make the overflow reset high. Otherwise, it will give the error overflow assertion failed.
Okay, others, your
Madam, in
answer?
this overflow reset, we are using non-overlapping implication. So that means when count equals to 16, the count should become 0 in the next clock cycle.
Okay. So here we have two type of implication. One is a overlapping and another one is a non-overlapping. So can you tell me what is the difference between both?
Ma'am, in overlapping implication, the consequent and the expression both should be true in the same cycle immediately. But in
Okay.
non-overlapping implication, we have one clock cycle delay. Like for example, if this count is equals to 16 is happening in one clock cycle, it should become 0 in the next clock cycle. So there is one clock cycle delay.
Okay. Yeah.
It's like giving #1 delay.
Yes. So here concurrent assertion property, we write within the property and end property or flow reset. So at the rate of posage clock and if count equal to all ones, then count should be equal to 0. And assert property overflow. Okay, so if overflow reset is high, that means it checks for this condition, else whatever the error, overflow assertion failed, counter did not reset to 0 after reaching to 15. Okay, and property increment by 1 at the rate of posage clock if reset is high and count should not equal to once, then count is equal to count plus 1. Okay, so here we are using overlapping and non-overlapping statement. That thing we will discuss again. And assertion property uh, pointing to the increment by 1 property. So if it is condition is satisfied, do the counting operation, or else increment assertion failed, counter did not increment by 1 as expected. So this is how we can write the concurrent assertion and immediate assertion. Okay, so a simple test bench. module counter, clock reset count, and here DUT, and generating the clock and initial begin, start counter test bench, and here if counter just a second. So here we have written immediate assertion also. Here it's not required. Okay, so to open the waveform, we can write increment assertion failed. Counter did not increment by 1 as expected. So at this point of time, assert property. So this assert error is printing. Counter is not incremented. And once from here, counter is equal to 15 and then 0 ending counter test bench. Overflow assertion failed. Counter did not reset to 0 after reaching 15. Here counter is resetting to 15. Counter is resetting to 0 after 15, right? So anyway, it doesn't print this statement. Okay, overflow assertion failed. Here it's not failed. And next error is increment assertion failed. Counter did not incremented by 1 as expected. So here it's printing and counter is running. Okay, so it will check at 15. So here also it's working correct. So this is how we can use the concurrent assertion and immediate assertion. Is it clear, everyone? So what are the main, what are the advantages and disadvantages? What are the use cases? Main difference between immediate assertion and concurrent assertion means immediate assertions evaluate immediately when the simulation reaches the line of code where they are placed. Okay, they execute and complete in a single simulation time, in a single step, similar to the traditional if else statement. Okay, so coming to the concurrent assertions, they are evaluated over multiple simulation time, not at a single time. Okay, they check the properties that unfold over time and also triggered by the specific clock events and also conditions in the design. So as we written the conditions here, based on that also we can check in the concurrent assertions. Okay, so suppose use cases, if you consider, like here is a counter. Okay, in the next session we will see some more examples, like how we can write for registers or some finite state missions to check for finite state missions, or any memory kind of example. We will discuss some use case. So as of today, so we can also check conditions that have some based on specific time, which evaluate some procedural blocks, so like function calls or assignments or state transitions like finite state missions. All these kind of things we can check immediate assertions. Okay, so concurrent assertions also same, like for protocol compliances or for handshake mechanism or for state mission transitions, we will check, we will use the concurrent assertions also. Okay, mostly the difference is like just we use in immediate assertions we use assert condition, as you've seen here, just assert condition. And concurrent assertions means we use property declaration with the event expression. So this is how the property declaration and also event expressions. Okay, so mostly immediate assertions used to check the value ranges, and these concurrent assertions are used to check the timing and protocols, just temporal checks. Okay, so any other differences we find? Immediate assertions means we use inside the procedural block, and concurrent assertions means we use outside the procedural block, not inside the procedural block. So if you see outside the always block, use the concurrent assertion. So that is one difference. Okay, clear everyone?
Ma'am, is it possible to write both concurrent and immediate assertions simultaneously?
We can write, no problem, but mostly we don't use both in one design. We can use either one only.
Okay.
Which one we can use most?
Which one you can use means now I told, right? Immediate assertions are mostly used to check the value ranges. Example, any signals. And concurrent assertions for mostly protocols. Both are used for finite state missions, registers, memories. Like we can use both, but evaluation is different. Immediate assertions means it uses a single clock cycle and evaluate immediately, but it takes some time across cycles and all, right? So mostly these are used for handshake protocols and state transitions. But here, a single value immediate means a single value transitions or to check the range we use. And also immediate assertions used in data processors to ensure that the input data is valid range or not. In that cases, we use immediate assertions. And concurrent assertions used to protocol handshake. Handshake means to check the, we have in I2C protocol there are acknowledgement signal and not acknowledgement signal, valid signals are there, right? So in that cases we use concurrent assertions to to confirm that acknowledgement signal follows the valid signal within a specified number of cycles, because it checks for multiple cycles, right? So that's why to ensure the protocol timing requirements, whether they require they met the requirements or not, we check in concurrent assertions. Okay, both are used in respective situations. So based on the verification mechanism, we cover both to check the instant value checks and also temporal behavior across the clock cycles. Okay, both are for validating design only. And in assertions, we have more topics. There are a lot of topics we will discuss one by one. Next thing is event scheduling. So as I already told, in system Verilog, we use event, like at what time each expression are going to sample. Okay, and execution wise. Assignment wise, there are different regions. First one is a preponed region and active region, inactive, non-blocking assignment region, observed region, reactive, inactive, postponed region. Okay, so in active region, all module process statements and it evaluates the continuous assignments. Everything will be executed in the active. Inactive means all zero delayed statements execute in the inactive region. Non-blocking assignment statements execute in the NBA region. Blocking assignments will execute in a blocking region. Observed region means assertions will be evaluated in the observed region. And also in reactive region execute the action blocks and programs, And in inactive, execute zero delayed statements in inactive and re-inactive. Dollar monitor, dollar strobe, PLI and VPI calls all execute in the postponed region. Dollar display execute in the active region. Okay, so if you want more clarity, you can check here. You will get detailed chart. So here is a detailed chart. So a time slot is divided into a set of 17 order region before time slot and after time slot. So suppose here it's a current time slot. So from previous time slot and after to next time slot. So how the executions are executing. If you see, these are all Verilog based. Okay, all are Verilog based, but in Verilog we have very less regions, active region, inactive region, and postpone, prepone regions. But in system Verilog we have these many: prepone, pre-active, active, inactive, pre non-blocking assignment, non-blocking, post non-blocking, like that: pre-observed, observed, post-observed, reactive, re-inactive, pre NBA, re-NBA, post-NBA, pre-postpone, postpone, like that. So if you observe detailedly in which region the SV commands are executing and blocking assignments, evaluation of or HS side values of non-blocking assignments and continuous assignment, dollar display statements all executed in the active region. Like that, input, evaluation of input and update the outputs of primitives done in the inactive. Like that, has zero blocking assignments in NBA region, and update the LHS values of NBA. RHS execute evaluating at active region, but update of LHS are done in the NBA region. Okay, so if you see in non-blocking assignment, what type of um, delays we use? We don't use a regular delay, right hand side we use the delays. So that is the only different execution and update. So you will find the difference, that is the main difference in blocking and non-blocking, right? So in the blocking, both will be done in the active region only, but in non-blocking assignment, RHS side evaluate in the active region, but update will come in the non-blocking assignment region. There is a delay difference is there. That delay difference you will find in this event chart. Okay, if you observe properly. And regions for new SV command, these all are new commands for new commands. And dollar monitor in the, I mean dollar strobe in the postpone. So these are different statements. Okay, so here detailedly mentioned, just go through the theory part. And in the next session, we will look into SBA building blocks and what are the different types of expressions. And we'll look into some examples also, some more immediate concurrent examples. And different simulator directives are there in assertions, like assert off, assert kill, assertion, dollar rose, dollar fell. These two mostly asked in the interview questions. So that's it for assertions. It will take some 2 to 3 sessions. And finally, we will discuss some project for coverage and the assertion. Okay, so hardly takes 4 days to complete assertions. That means 1 week. Okay. So any doubts still here, everyone, on today's session? Is there any doubts?
No doubt from my side.
Others?
No, ma'am.
No, ma'am.
Okay. So coming to APB protocol, if you have any doubts, we will discuss. because you already know system verilog, right? No need to explain point to point. From tomorrow, we will, Tuesday, from Tuesday, we will start AHB protocol. Okay. So everyone be clear till APB. Whatever the doubts you have, clarify your doubts. So we will start AHB. Did you observe the output, everyone, for APB? Sanjay?
Ma'am, no, ma'am. I just give a brief idea about that system lab code for APB.
Okay, okay. Do you know how to write the test bench, a system verilog test bench?
Yeah, madam. But some extra modules, ma'am, like header switch. What are that, ma'am? Like,
We'll discuss.
I know that architecture, ma'am. Like,
Okay, okay. So I think I already explained the waveform, right? Address at 11, you are storing 66, right? Data for 1790, for 1580, 1472, 1897. So at read side, for 17, read data is 90. So it's correct. For 17, 90. For 20, at write address, we are not storing any data for 20. So we got an ANet output for 1472. So for 1472 is correct. And again 1790 is correct. Okay. So we are getting proper write data and read data. So you need to check here when the write signal is high. Whenever write signal is high, write data is happening, and whenever write is low, here read data. Okay, so reset is high, and you can check the phases also, setup phase, active phase, access phase. Okay, so coming to the code. So first start with the transaction class. Okay, so here is the transaction class. So in the transaction class, we need to declare all the input and outputs. Inputs must be declared with a rand keyword because we do the randomization in generate block, and outputs will declare with same data type. No need to mention the rand because outputs are not randomized. Only inputs will be randomized, right? Next, we need to write the constraint, any constraint, inside constraints or inline constraints or soft constraints. So what is the practical example of soft constraint? Suppose here main constraints are there. Okay, so 10 to 20 address, p address is 10 to 20, right address is 50 to 100. Between that we need to generate, that is the main constraint. Okay, so without changing this constraint, okay, I want to take some new constraint. Okay, like a p address must be equal to 15, and p write data equal to between um, 60 to 100 or 60 to 80. Okay, so I don't want to remove this, I just want to override these constraints with some inline constraint. Okay, so how I can override those constraints with this constraint? Can you tell
Madam,
me?
this constraint has to be declared as soft, and then we can use with keyword. For example, p address is there, so we can write p address with item greater than 20, value greater than 20. So that will override,
Oh,
madam.
okay, okay. Others, any answers?
what's
Okay,
what's the question?
who asked?
Question, ma'am. Question. Repeat.
Okay. So what I'm telling is these are the main constraints. Okay. So suppose here what are the constraints? P address must be 10 to 20, P write data 50 to 100. Okay, those are fixed constraint, main constraints. I want to override this constraint with some new constraint. Okay, like P address equal to 15. It should generate 15. P write data equal to 60, suppose. Okay, so without changing this, without removing these constraints, just I want to override this constraint with a new constraint. So how I can do that? It should not, these constraints should not repeat, should not print. Okay. In place of this, new constraint should execute. How I can do that?
Using soft keyword.
How we can use the soft keyword? How soft keyword is applicable here? Or not the syntax? Okay, so here in P address we can write the soft here, so you can go through the syntax and so how we can override means we can write here itself, or mostly inline constraint means we will write with the um, randomize method, right? Near randomize method. So here tr dot randomize of with here inline constraint you can use. By using that you can mention P address and P write data with a new value. Okay. And in the transaction class mention as a soft constraint. So automatically it will do the override with a new constraint. Okay. So that's what application. So first transaction class is completed, and generator, in generator we do the randomization rand transaction tr. First we create the transaction class and then mailbox and then constructor task repeat here we need to create the object for transaction class and tr dot randomize, and here mailbox and display statement for generator which we declared in the transaction class, and display the um, mailbox num method, that means how many transactions. Okay. And after generator block, driver is nothing but here we set the path. Why? Because here we do the interfacing, right? By using virtual interface is used. What is the difference between virtual interface and interface, Sanjay?
Uh, Interface, physical interface is means static man. We can't change the values or anything for simulation.
Mm.
Virtual interface is dynamic. Since all classes are in SV test bench architecture are dynamic, so we can use virtual interface man. That virtual interface pointer is always pointed to physical interface man.
Okay. So what is the difference between clocking block and mod port?
Smart port is nothing but particular ma'am. We can mention the uh, signals ma'am. Signals. Which signal is connected to which port? That like particularly we can mention it ma'am. Smart ports.
Okay.
Clocking block means we can eliminate the race around condition. Like at particular clock only we can pass the signals ma'am. Like that only.
Mm. So just for synchronization between driver to DUT to monitor, because different blocks are there. So for more synchronization purpose, we use the clocking block with a skew. Okay. So here I think you already know how to set the path, right, to clocking block. So whatever the variables we want to access, we access through the mod port and clocking block only. So first reset task, and then one task is for write operation, other task is for read operation, and next in write task how we are writing the transaction data into the DUT. So here drive IOF is the macro, and tr dot p address, tr dot p write data, tr dot again P address. These are nothing but randomized data. That randomized data we need to send to the DUT via interface via this path. Okay, and read side also all enable signal, write signal, and a P address signal, read address we are sending to the DUT. From the DUT we are getting the read data. Okay, so that is what we need to mention in the driver. And then monitor also same as a driver, but just reverse. In the driver we done with driver to DUT, but in monitor DUT to monitor. Okay, so DUT to transaction class. So that's what we mentioned here. And here scoreboard I didn't mention the logic. Just try yourself. Just we need to check here. Write address should be equal to read address. Write data should be equal to read data. If not equal, you should get the error. Okay, so just mention that condition. If you don't get, I will share the code. Okay, and all these modules we connect in the top level environment. In the environment top level, we will call all main task of generator, driver, monitor, scoreboard. And next, for environment, we have test, top level test. Here, test.sv. So in the test.sv, we call the environment run task. This test.sv will be called from main test bench top level. Okay. So here header.sv is nothing but actually in the environment, if you observe, we need to mention all submodules here, include generator.sv, monitor.sv, scoreboard.sv, driver.sv, like that we need to mention because it is taking the files from different blocks, right? So we need to include all the sub files in the main block. Okay, that's why we need to mention, but without mentioning like that, we can create one header file, okay, for all common file. So here we can mention all the files. We can include all the files here. So interface.sv, app/slave.verilog file, and transaction.sv, generator, driver, monitor, scoreboard, environment, test. All files are included here. And this header file is included in the top level testbench.sv. Okay, so that if you don't include here, what happened? Mainly in EDA playground, main file is a testbench.sv. It will run that main file. Okay, so if you don't include that here, it doesn't run. Okay, if you don't want to take header file, you can include all the separate file in the main modules of each module. Like environment means it should include driver, generator, monitor, scoreboard. Like test.sv means it should include environment. Okay, in transaction class no need to include, and also in interface no need to include. In testbench.sv you can write main test bench. That is one format, or else you can create one separate header file, or you can include like this. Okay, so if you have any doubts, let me know. I can explain you some other code. Okay, I will share you some recorded session also for APB protocol if you want to understand more into the test bench. Okay, and for AHB protocol and AXI protocol, we will discuss in a UVM code. Okay, UVM verification.
I have one doubt, ma'am.
Yeah, tell.
How we will write the reference module for scoreboard, ma'am, in scoreboard, like golden DUT, like
Reference module. That's what I told. Okay, wait, let me show for some other example. For FIFA example, I'm showing same like this. You can mention in the APP protocol also. Okay, so here if tr.read is high, so write and read operation cannot be done at a time, right? If write is high, write operation. If write is 0, read operation. In APP protocol also same. In APP protocol, how you will mention what is the write read signal here? So P right. So if P right is high, then write operation. If P right is low, read operation. Okay. So here also same. If memory buff, MEM means name of the memory of write tr dot read pointer is not equal to tr dot output. Okay. Then it should generate expected value. If read pointer is not equal to data out, and it should generate the error, that is it is not expected value, it should generate the error. If both are same, it should generate the expected value. Okay. Else if tr dot write is high and buff memory p write pointer is equal to data in. So here number of transaction plus plus, or else how you can write here, you can compare with the write data, read data. If pure write data and read data both are same, then expected value. And write address, read address both are same, expected value. Else it is not expected value. Like that if else conditions you can mention. Okay.
Okay, ma'am.
Excuse me, ma'am.
Yeah, tell me.
Ma'am, one small doubt. In driver, we are using for packet to pin conversion, we are using non-blocking assignment. Whereas from pin to packet conversion in monitor, we are using blocking assignment. Why are we doing that?
Um, it's not like that we can use a non-blocking assignment for both.
Okay. Because the similar pattern I've seen in other project also. So suddenly I got doubt. Okay, like why we are
Okay.
doing in that way only. Okay,
No,
madam.
it's not like that. We can use any.
Okay, ma'am. Thank you.
Okay. Others, any doubts? So that's it for today's session. Okay. So I will
Okay, ma'am.
share you the codes and I will update the session. Just go through that, okay? And work on immediate assertion and concurrent assertions. And I already shared the assignment also on assertions. So start working on that questions. Okay. Thank you all. Bye.
Thank you, ma'am.